You ever write a simple piece of code, maybe just hello world, and really stop to think about how that text actually gets onto your screen? Or, you click on an icon and this whole complex application just springs to life. It feels like magic, right? But it's not. There's this incredibly powerful invisible layer sitting between your software and the physical hardware, acting as the master translator. And today, we're going to pull back that curtain.
Today, we will deeply understand Chapter 2, Operating System Structures. We're going to get right into the heart of what makes your computer tick. We'll look at its fundamental structure, the services it provides, and exactly how it makes everything you do possible. It's the foundation for everything that comes next, so let's get started.
So here's our game plan. We're going to start from the outside, from your perspective, and work our way deeper into the machine. We'll kick things off with OS services, what the OS is actually doing for you, kind of like a butler. Then we'll look at the interfaces, how we actually talk to it. From there, we open the magic door, system calls. This is the secret language that programs use to ask the OS for help. Then, we'll put on our architect hats and look at the actual blueprints, the different ways an OS can be built. And we'll wrap up by looking at the life cycle of the OS, from the moment you hit the power button.
All right, so first things first. What does an operating system really do? The best analogy is to think of it as the ultimate assistant. It's part butler, part city government, part security guard. Now, it's not going to write your code for you or browse the web, but it provides the perfect, stable, and efficient environment that allows your applications to do that work. It's truly the unsung hero working tirelessly behind the scenes.
Now, these services really break down into two big categories. First, you've got the stuff that helps you, the user. The user interface is the most obvious one. It's the windows, the icons, the mouse pointer, or maybe a command line. Program execution, that's the magic of taking a dead file on your disk and breathing life into it, turning it into a running process. I/O operations are how your super-fast processor has a conversation with your incredibly slow keyboard or your printer. And the file system, that's just a beautiful illusion, making you think you have neat folders and files, when really it's just a managed chaos of ones and zeros on a disk. But then, there's this whole other set of services that the OS provides for itself just to keep the system running smoothly. Resource allocation is the OS acting like a strict parent, deciding which of your 50 browser tabs gets a slice of CPU time. Protection and security is the bouncer at the club door, making sure your game can't peek into your banking app's memory. And error detection is the system's own immune system, constantly checking for problems. It's like the power grid or the plumbing in a city. You don't think about it when it's working, but you would absolutely notice if it suddenly disappeared.
Okay, so if the OS is our all-powerful butler, the next logical question is, how do we give it orders? How do we communicate what we want it to do? Well, that's where interfaces come into play.
For us humans, there are basically two main ways we can talk to the OS. First, there's the command line interface, or CLI. Yeah, that's the classic hacker in the movies, text on a black screen interface. You type in very specific commands and the computer just does it. It might seem old school, but for developers and system administrators, it's incredibly powerful, fast, and amazing for automating tasks. And then you've got what most of us use every single day, the graphical user interface, or GUI. This is the friendly world of desktops, windows, icons, and dragging things around with a mouse. It's intuitive, visual, and much easier to learn. Look, neither one is better than the other. They're just different tools for different jobs, like a power saw versus a hand chisel.
And of course, it doesn't just stop with the mouse and keyboard, right? On our phones and tablets, we've moved to an even more direct way of talking to the machine. Touchscreens. We're literally tapping, swiping, and pinching our commands directly onto the interface. It just goes to show how these interfaces are always evolving to feel more natural, to feel more like an extension of us.
Okay, so that's how we talk to the OS. But what about our programs? How does Chrome ask the OS to draw a window? For that, they use something called an Application Programming Interface, or API. Here's the best analogy. When you go to a restaurant, you don't barge into the kitchen and start cooking. You're given a menu and you place an order. The API is that menu. It's a list of all the services the OS offers, like create a file, draw a button, get network access, and it defines exactly how a program is supposed to ask for those things.
So if the API is the menu, what happens when your program actually orders something? That is a system call. A system call isn't just a regular function call in your code. It's the moment your program formally knocks on the kernel's door and asks for a service. It is the fundamental, direct way to request help from the operating system. This is the transition point, the magic door between your program and the all-powerful OS kernel.
Let's make this totally concrete. Think about something as simple as copying a file. To you, it's a simple drag and drop. but underneath, it's a storm of system calls. The program makes a system call to display a prompt for the input file name, then a system call to read what you type on the keyboard, then more system calls for the output file name, then a system call to open the first file, another to create the second file. Then it starts a loop, system call to read a chunk of data, system call to write that chunk, again and again, and finally, system calls to close both files. One simple action from you triggers a whole cascade of these fundamental requests.
So what actually happens during one of these calls? This is one of the most important concepts in operating systems. Your computer operates in at least two modes. There's user mode, which is a restricted, safe sandbox where your applications live. They can't just do whatever they want. And then there's kernel mode, where the operating system lives. It has unlimited, godlike access to all hardware. A system call is the only legal way to cross that boundary. When a program makes a system call, it executes a special hardware instruction called a trap. This trap is a signal to the processor to pause the user program, switch into the all-powerful kernel mode, and hand control over to the OS. The OS does its work, and then carefully switches back to user mode and returns the result. This strict, controlled crossing is what keeps our system stable and secure.
Okay, but wait. If the program is asking the OS to open a file, it has to tell it which file, right? It needs to pass along some information. There are basically three ways to do this. The simplest way is to just put the parameters directly into the CPU's registers, but there's not much space there. If you have a lot of data, you can put it all into a block of memory and then just pass the memory address in a register. It's like saying, hey, all the info you need is over there. The third common method is to push all the parameters onto the program's stack, and the OS knows to just pop them off when it takes over.
So what kinds of things are we asking for with these system calls? Well, you can pretty much group them into a few big buckets. There's process control. That's things like creating a new process or ending one. There's all the file manipulation stuff. Create, delete, open, read, write. Device manipulation lets you talk to hardware like a printer or a camera. Information maintenance is for asking things like, hey, what time is it? Or how much memory is free? Then you have communications for sending messages, maybe over a network. And finally, protection, which is all about controlling who gets to access what. Basically, anytime your program needs to touch the outside world, it's got to make a system call.
All right, we've seen what the OS does and how programs talk to it. Now let's go one level deeper. Let's put on our engineering hats and look at the actual internal blueprints. How are these massive, complex pieces of software actually structured? Before we look at specific structures, there's a really important design principle we need to understand: the separation of policy from mechanism. Policy is what you want to do. For example, a policy might be, give high-priority jobs more CPU time. Mechanism is how you're going to do it. The mechanism might be a specific scheduling algorithm that uses a timer. By keeping these two separate, the OS becomes incredibly flexible. If you decide you don't like your scheduling mechanism, you can swap it out for a new one without changing your overall goal, your policy.
So if you go way back, the first operating systems were, well, let's just say they were messy. They used what's called a monolithic structure. Basically, the entire OS was just one giant tangled program. Everything could call everything else. This made it really fast, for sure, but it was incredibly fragile. A bug in the printer driver could overwrite memory being used by the file system and bring the entire computer crashing down. It was the Wild West.
So, to bring some order to that chaos, the next big idea was the layered approach. And you can literally think of it like a layer cake. At the very bottom, layer 0, you have the hardware. On top of that, you build a layer that handles, say, memory management. On top of that, a layer for managing processes, and so on, all the way up to the user interface. The rule is, a layer can only talk to the layer directly below it. This is much more organized and way easier to debug, but it can be less efficient since a request might have to travel down through many layers.
This leads us to one of the biggest philosophical debates in OS design, the monolithic kernel versus the microkernel. A monolithic kernel, which is what Linux is like a high-performance race car. All the core OS services, scheduling, file system, networking are bundled together into one big kernel. This makes communication between them super fast. The downside? If one component has a bug, the whole kernel can crash. The whole car goes off the road. A microkernel, on the other hand, is like a super safe modular vehicle. The kernel itself is as tiny as possible. Its only job is to manage communication between other services, like the file system or device drivers, which all run as separate programs out in user space. This is way more reliable. If the networking service crashes, you can just restart it. But you pay a performance penalty, because all these separate pieces have to constantly send messages back and forth through the kernel. It's the classic trade-off, speed versus safety.
So who won the debate? Well, the truth is, most modern systems kinda cheat. They take a hybrid approach. For example, macOS and iOS have a microkernel at their core, but they also run a lot of services inside the kernel for better performance. And even though Linux is monolithic, it uses something called loadable kernel modules. This means you can dynamically load and unload pieces of the kernel, like drivers, without rebooting. So you get the flexibility of a microkernel design with the raw speed of a monolithic one. It's the best of both worlds.
All right, last major topic. We've seen the blueprints, we've seen the architecture. Now let's talk about the OS's life, from the moment it's born to how we keep it running healthily.
Have you ever really thought about what happens in those few seconds after you hit the power button? It's a fascinating choreographed dance. First, a small program stored in firmware on your motherboard called the bootstrap loader wakes up. Its one and only job is to find the operating system kernel on your hard drive. Once it finds it, it loads the kernel into memory and basically says, okay, you're in charge now. The kernel then takes over, initializes all the hardware, starts up the essential system processes, and finally gets the system ready for you to log in.
Of course, things don't always go perfectly. We've all seen a system crash. When that happens, the OS has tools for debugging. It can produce something called a core dump, which is a snapshot of the entire contents of memory at the moment of the crash. It can also generate detailed log files that trace everything that was happening leading up to the failure. It allows developers to act like digital detectives, performing a post-mortem to figure out exactly what went wrong.
And it's not all about fixing crashes. The OS also provides tools for performance tuning. You've probably seen something like the Windows Task Manager or the Activity Monitor on a Mac. These give you a real-time dashboard of your system's health. You can see what's eating up your CPU, what's using all the memory, and what's hammering your disk. In fact, if you have it handy, you should open it up right now and just take a look. It's the OS giving you the power to see what's really going on under the hood.
So, we've covered a ton of ground. We've seen the services an OS provides, how we talk to it, and how it's built. But this incredible structure just sets the stage for the real magic. The big question is, how does the OS use this structure to run your web browser, your music player, and your code editor all at the same time, without them turning into a chaotic mess? How does it juggle them all so perfectly? Well, that is the topic for our next discussion, when we dive into the world of process management.